Welcome to the next class. Last time we have successfully finished the pretty big topic of self-replication in artificial systems. And hopefully we have, let's say, finished with the motivation that before we can understand the biology of artificial systems, we should understand the physics of artificial systems, that is the underlying dynamical systems of these artificial worlds. And as we have seen many examples of constructions within cellular automata, hopefully that shows that they are rich enough, that they are worth our concern for the next big part of the course. So today will be, let's say, an introductory lecture about the basic properties of the cellular automaton space. So let us fix for now SCA with states S in dimension D and some global rule F with the underlying neighborhood and local rule So this we already defined, so just a bit more of some basic terminology. So for a configuration C from the configuration space, we call the sequence C, FC, F2 iterations of C, and so on. The trajectory of A with initial configuration C. If this sequence ever becomes periodic, we call its pre-period the transient and the periodic part, the limit cycle. And finally, a space-time diagram with initial configuration C is just a matrix whose rows are exactly the consecutive elements of the trajectory. So is a matrix whose consecutive rows are exactly C. So this is pretty standard. We have already seen a lot of space-time diagrams. So let's move on to the next important topic, which is shifts and periodicity. So let V be a d-dimensional vector with integer coefficients. We define the shift map for every configuration C and W as the image of this configuration at position W is just the shifted configuration. So, example, in 1D, the shift map sigma 1 just takes every configuration and shifts it by one position. So hopefully this is clear. The shifts will be an important ingredient when studying cellular automata, because cellular automata are exactly maps that are continuous and that commute with the shifts. So let's make an important observation. For every vector V, we have that any global map of a cellular automaton would commute with this shift. So this is extremely easy to verify. You can do this if you have time in the exercise sessions, but intuitively, the reason for it is that when we define F, we rely on this local rule that we apply uniformly to all sites. So F does not, when it maps when we look at the ith position of its image, this image does not rely in any way on the exact position of the cell, just on its relative neighborhood. So, are there any questions? Okay. So this leads us to one very natural subset of configurations to consider, which are the totally periodic configurations. So suppose we have a configuration. We say that C is totally periodic. If there exists a sequence of linearly independent vectors and particularly d of them such that if we shift this configuration, it stays invariant for all I. So another extremely simple example. Again in 1D, for instance, a configuration that just periodically repeats the pattern 0, 0, 1, 0, 0, 1. Is totally periodic. Here the basis, or let's say the basis that spans this d-dimensional sublattice is simply just the vector that shifts this by 3 cells. So we denote by totally periodic, which is a subset of z s to z to the d, the set of all periodic of all totally periodic configurations. And here the crucial observation, what makes this subset of the full configuration space natural, is that if we restrict the global rule of SCA to this subset, it is a self-map of this. So the total periodicity of a configuration is preserved under the image of F, and in particular, if we restrict F to this subspace, then we have a map like this. So maybe we can quickly verify this so that I prove something today. So let C be invariant under sigma v for some vector v. So let's look at the image of this configuration and what happens if we shift that image. So we can use the fact that this global map commutes with the shift. And since C is invariant under the shift, this is just so one way where this becomes useful is I have briefly mentioned that when we study cellular automata, it's very nice that we can visualize the dynamics or the space-time diagrams by generating them on a computer. But in that setting, we actually need just a finite space to study. So I talked about this cyclicity of the configurations. And this is indeed how you can view the dynamics of many cellular automata. But so let's formally define that. So cyclic CA global map. So let so let us fix some size of this finite cyclic grid. We define the cyclic global map of A we can denote it by F. Okay, this is I guess M. Okay. Fm to be a map from the finite space into itself MD. So this is essentially all the configurations of this finite torus that we talked about. So in 1D it would just be a loop. In 2D it would be a two-dimensional like discrete torus. As follows. So for some configuration C, which is now just a finite object, and some position I if we want to look at what's the image of C at this position I, then again we will just apply the local rule of the CA to the position I plus the first vector that specifies the neighborhood. But now this might not necessarily be an element of this ring, so we just take it modulo M. So here we should deserve a terminology window. Oops. So if we have two vectors, I don't know, V and M from Z to the D, V is some V1 up to VD, and M is some M1 up to MD. Then if I do this V modulo M, it's literally just coordinate-wise. So that's what's happening here. We're just ensuring to look back in to get an element from here, and we do this for all the neighborhood positions. Yeah. So an example. So for instance, for game of life, and M being, for instance, 5, 3. Okay, 3, 5. So this is our Z3 times Z5. And now if we assign to each cell some values 0 or 1, then this becomes an element of and in this is what I drew last time, is essentially this line. We identify it with this border, and this border we identify with this border. So I think it's pretty clear. So if we want to, I don't know, compute the neighborhood of this particular cell, then for these 3 neighborhoods, in the Moore neighborhood, it's pretty clear. But for instance, if we want to compute the south neighbor of this cell with coordinates 2, 4 is, so can you tell me what are the coordinates?
0, 4.
Exactly. Perfect. So this is pretty clear, hopefully. But this is a pretty different mode of operation than the global rule. So just to formally check what's going on, you will have an exercise for this. But in some sense, the exercise will say that every finite cyclic configuration you can unravel onto an infinite one, such that the dynamics on this subspace is essentially completely equivalent to the, or the dynamics of this finite cyclic global rule on the finite configurations is equivalent to the dynamics of the original infinite map restricted to this finite set of totally periodic configurations. So this is just to keep in mind that when we look at these cyclic spacetime diagrams, we do see something, or it tells us something about the actual infinite map, just restricted to some subspace. So what I mean by equivalent dynamics is the last standard definition. So isomorphic dynamical systems. Thank you. Thank you. Isomorphic dynamical systems. Yeah. So consider dynamical systems. So we can formulate this in full generality and YG. So here I just mean F is a self-map of X, and G is a self-map of Y. We say they are isomorphic if there exists a bijection phi from X onto Y such that we have that, yeah. Or if you like to look at commuting diagrams, we have F, we have G, and we want this diagram to commute with phi. Yeah. So in particular, phi gives us a way, like, or a correspondence between trajectories of F and trajectories of G, which we just start from the images under phi. So G phi C G squared C. Simply by mapping this trajectory onto this trajectory by phi. Yeah, so you can kind of see the second iteration follows because we can extend this diagram and so on. So in this sense, we can say that the dynamics of F and G are equivalent. Up to this relabeling, they kind of do the same thing. So a remark is that we will revisit this definition actually twice as we enrich the configuration space of the cellular automata with more and more restrictions. So once we introduce a topology on the configuration space, it will be meaningful to require that this phi is not only a bijection but a homeomorphism. And then when we will study the computational capacities of cellular automata, it will be meaningful to require that this phi is some computationally reasonable mapping. Like if this phi solves the halting problem, then it's a bit tricky to say that there is some computational relationship between two cellular automata if the way we translate between them is computationally infeasible to implement. Good. So in some sense, one of the exercises will be to show that this dynamical system is isomorphic to a particular or a restriction to a particular subsystem of the original cellular automaton. Nice. So we can move on to the next tiny chapter, which is parametrizing the CA space. So we still suppose we have our cellular automaton with some neighborhood n, and we can make a small observation that we can interpret A to be a CA with a larger neighborhood in a pretty straightforward way. We just extend the local rule to these extra coordinates in a way that it's completely independent on the values there. So this poses one particular issue. Suppose I give you some global map, and I ask you whether this is a cellular automaton. This essentially means you have to find a neighborhood and a local rule such that you will express this global map with respect to this local rule. But from this observation, it is clear that the choice of neighborhood is not unique. Actually, you have infinitely many choices. So it's nice to make some canonical choices. So as the choice of CA neighborhood is not unique, there are two canonical choices. So either we choose n to be minimal, there is no strict subset of n would give you the CA, or we choose n to be symmetrical. So this will be our choice, typically, because in this way, the neighborhood is parameterized by a single value R. So what does this mean? So this will be a good moment to add another. Maybe I already said this, but let's just consider the norm to be just the maximal. We say a neighborhood has radius r if, or I can even say this without the norm, but okay, if or equivalently, we can just write that n is a box like this. And the thing is, if we only restrict ourselves to study cellular automata with symmetric neighborhoods, we actually don't really restrict ourselves, because we can interpret every CA as a CA with a symmetrical neighborhood. And we choose R to be minimal. So this finally brings us to the first playground when you observe the behavior of cellular automata. Okay, we can conclude that thus we can parameterize the CA space by just 3 values: the number of states, the dimension, and the radius. So one of the smallest classes that we can study, which has some non-trivial behavior, is the class of elementary cellular automata. Which is the class with just binary states, which I will sometimes just denote as 2. Dimension 1 and radius 1, which means there are 256 of them. The number of neighborhood configurations is 2 to the power of 3, and then for each we have a choice of the outcome of the local rule, so it's 2 to the 2 to the 3. And we typically refer to each by its Wolfram number. It's just the terminology introduced by Stephen Wolfram. So if we have a local rule, its Wolfram number is, you essentially order the inputs of the neighborhoods by interpreting them as binary numbers, with this being the most important digit. And you look at what is the outcome, and then you scale it by growing powers of 2. 2 to the 1. Yeah. So for instance, let's take the map, which is just A plus C modulo 2. So we can look at its rule table. This is the problem of the blackboard, that when I fill a space, it would be typically in your, typically 1 corresponds to a black color and 0 to a white color. But I write it the same way you would write it, so essentially every filled space is a 1. But this is, so here what do we have? This is a 0, this is a 1, and this is a 0. So it's 2 plus 8 plus 16 plus 64, which is 90. So then we would refer to this F as rule 90. And you will see this a lot in the notes. Is this clear? So this is one of the rare classes where we can really exhaustively look at every single cellular automaton in this class to get some first intuition for what kind of behavior we can observe. And the person who probably did this in the most meticulous way was exactly Stephen Wolfram, who did observe a lot of space-time diagrams of some of the most compact, or some of the cellular automata with the most compact descriptions. And he proposed the so-called Wolfram's classifications, where essentially he would claim that every cellular automaton behaves roughly to one of the 4 qualitative behaviors determined by 4 classes that he defined. And though this definition is, or like this classification is informal and it's just a heuristic, it is still useful to gauge some first intuition of what types of behaviors we can see. So I think I will show this to you after the break.